Welcome, curious minds, to another deep dive. Today we're taking a magnifying glass to something so fundamental it often gets overlooked: Newton's first law of motion.
Mm-hmm.
It's often presented as simple, almost obvious, but as we'll unpack today, it holds a surprising depth and has been the subject of fascinating debates for centuries.
Indeed, yeah. While it might seem like just a basic building block of classical mechanics, a closer look at Newton's first law reveals really profound concepts about time, space, force, and motion.
Right.
Our mission today is to explore the layers of interpretation and the deep philosophical and practical questions it raises, showing you how understanding this foundational principle can illuminate not just classical physics, but also connect us to more advanced theories of the universe.
And you shared some incredible sources with us for this deep dive. I mean, everything from the foundational text of the laws of Newton himself to really insightful discussions on his philosophical underpinnings and, modern interpretations.
Yeah, there's a lot out there.
So we'll be extracting the most important nuggets of knowledge and insight, guiding you through the historical evolution, the surprising contradictions, and the enduring challenges associated with this seemingly straightforward law. So buckle up, because we're about to explore the hidden complexities of a principle you probably thought you already knew inside and out. Okay, let's unpack this then. The first law, often called the law of inertia, states that everybody continues in a state of rest or uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it.
Right.
On the surface, it seems almost self-evident, right? Like a ball just keeps rolling unless something stops it.
Mm-hmm.
Pretty basic. But here's where it gets really interesting.
Mm-hmm.
Despite its apparent simplicity, the understanding and interpretation of this law have been subjects of, extensive debate throughout history. This diversity of views points directly to a lack of consensus in its precise understanding, highlighting a deep-seated need for rethinking fundamental concepts in mechanics, even centuries later.
You've hit on the core paradox of the first law there. It's elegantly simple in its phrasing, yet incredibly complex in its implications and its relationship to the rest of physics.
Yeah.
The fact that brilliant minds have spent centuries arguing over its exact meaning tells us there's much more to it than meets the eye. It's not just Physics 101.
Definitely not. Let's look at some of these diverse views, because they really paint a picture of just how complex the simple law actually is. For instance, the philosopher of physics Tim Maudlin suggests it's only a slight exaggeration to say that all of Newtonian physics is implicitly contained within the first law.
Whoa!
Think about that for a second. He's saying that this seemingly simple statement about an object's tendency to resist changes in its motion somehow encapsulates the entire framework of Newtonian mechanics.
That's a huge claim.
It elevates the first law from a mere starting point to a foundational principle with immense hidden content.
What's fascinating here is how Maudlin's perspective emphasizes the first law's profound content, suggesting it's not just a descriptive statement, but a deep structural principle.
Right. If the first law truly contains all of Newtonian physics, then it implicitly defines concepts like force as precisely that which causes a deviation from uniform motion.
Okay.
And it also defines an inertial frame as the specific context in which this definition of force holds true. So instead of thinking of the first law as like a mere preamble to the more famous ESMA,
Which is how it's usually taught, right?
exactly, Maudlin forces us to consider it as the bedrock, with ESMA then becoming a consequence of that foundational definition. This would require a significant mental shift in how we approach and teach classical physics, perhaps starting with defining what is not a force before defining what is a force.
Wow. So if the first law truly contains all of Newtonian physics, what does that mean for how we teach physics? Should we start there rather than with ESMA? What kind of mental shift would that require from a student? It almost feels like a philosophical statement dressed as a physical law.
Precisely. It challenges the conventional pedagogical approach. If you start with ESMA, the first law often appears redundant, kind of unnecessary.
Yeah, just the Evler case. Right. But if you see the first law as defining the very stage on which FMO plays out the stage of inertial frames, where forces actually mean something, then its independent significance shines through. It's a foundational definition, not just an observation.
That's a fascinating distinction. But then, in stark contrast, you have Sir Arthur Eddington, who famously quipped, "Everybody continues in its state of rest or uniform motion in a straight line, except insofar as it doesn't."
Yeah.
That's a humorous, almost mocking statement. But it highlights a very real conceptual challenge. Eddington's sarcasm points to the perceived emptiness or tautological nature of the law. If it just tells us what happens unless something else happens, is it truly a law or just a circular definition? He certainly didn't pull any punches, did he?
He certainly did not. Eddington's quip challenges the first law's empirical content. His point is that if any deviation from uniform motion can simply be attributed to an unseen force, or if we just define force as whatever causes motion to deviate from straight lines, then the law becomes unfalsifiable.
Right, you can't prove it wrong.
Exactly. It's true by definition, but it doesn't actually tell us anything new about the real world. It's like saying all bachelors are unmarried men. It's undeniably true, but it doesn't give you any new information about a specific person or the state of the world. It's an identical definition, a tautology.
And then Ernst Mach, another prominent figure, he redefined the law of inertia by focusing on the interaction of bodies with each other, rather than on force.
Oh, Mach, yeah.
He stated that the law of inertia merely expresses that a body sufficiently distant from other bodies remains in a state of rest or uniform motion in a straight line. He's trying to make it more empirically grounded, right, by replacing the abstract concept of force with the more tangible idea of distance from other bodies.
Right, trying to get rid of the unobservables.
But in doing so, he exposes its practical inaccessibility.
Exactly. Mach's redefinition attempts to remove the unobservable force from the definition, replacing it with the more tangible concept of distance from other bodies. His argument was that if you have a truly isolated body, far from all other matter, then its motion will be uniform. This makes the law observational, in principle.
In principle.
In principle. But, as you rightly pointed out, it immediately runs into the problem of practical verification. Can we ever truly find a body that is sufficiently distant from all other influences, especially long-range forces like gravity or even, the collective gravitational pull of the entire universe?
Doesn't seem likely.
Not really. This very point leads us to later challenges we'll definitely discuss. Mach was highly influential, though, in pushing physics away from unobservable absolutes and towards empirically verifiable concepts.
So we've wrestled with these philosophical giants and their varied interpretations. But then you have Henri Poincaré, who took an even more radical stance, believing the first law is not a fact of experience. It is a generalization and a convention to some extent.
Ah, the conventionalist view.
Right. He views it not as an empirical truth derived from observation, but as a fundamental assumption that shapes our theoretical framework.
No.
It's a choice we make to build our physics, almost like picking a set of rules for a game before you start playing.
Exactly. Poincaré's view is profound because it suggests that some of our most fundamental laws might actually be conceptual agreements or conventions that we adopt because they lead to simpler, more powerful physics.
No, convenience in a way.
Well, useful convention. If it's a convention, then we're not discovering a truth about nature, but rather building a useful framework for understanding it. This really highlights the interplay between philosophy, mathematics, and empirical observation in the development of scientific theories. It's not just about experiments.
It truly is a kaleidoscope of interpretations, isn't it? From Maudlin seeing it as encompassing everything, to Eddington seeing it as almost nothing, to Mach's empirical focus on distance, and now Poincaré's convention. What does this wide array of views tell us about the very nature of this foundational law?
This spectrum of thought isn't just academic hair-splitting. It reveals the profound conceptual complexities of the first law. Is it a mere definition, an empirical principle, or does it carry deep physical content that dictates the very existence of inertial frames?
These are big questions.
Huge. And these questions not only help us better understand the first law, but also highlight the need for a more coherent framework for the analysis and teaching of classical mechanics, particularly as we try to bridge the gap between classical and modern physics.
It feels like we're wrestling with foundational definitions here. If even the textbooks can't agree, where does that leave someone trying to truly grasp this law? Now, let's compare Newton's original formulation with how it's presented in modern textbooks, because even there, the plot thickens.
Oh, definitely.
Newton's original formulation in Principia states, everybody continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. Interestingly, Newton's concept of force here is actually closer to what we now call impulse.
Right, like a sudden hit.
Yeah, change in momentum over a small time interval, often associated with collisions. He then generalized this idea to continuous forces, even action at a distance, like gravity.
And this is a crucial distinction that often gets lost in modern teaching. Newton's original force-impressed concept was very direct, akin to a push or a pull, or the immediate effect of a collision. Imagine hitting a billiard ball that's an impressed force.
Okay.
the generalization to continuous forces, like the constant pull of gravity on a planet or action at a distance forces, was quite a conceptual leap from his initial, more direct understanding. It broadened the scope of force considerably.
Right. But then look at how many modern textbooks present it. For instance, Halliday's textbook presents the first law as, if no force is exerted on a body, its velocity remains constant, i.e. it has no acceleration. Morin offers a similar statement. A body moves with constant velocity, which may be zero, unless a force is exerted on it.
Pretty standard stuff.
Yeah, and in both cases, the first law is often introduced as a special case of the second law, EFMA, where if F0 then H0 0, potentially diminishing its independent significance.
And this is where much of the confusion arises for students. Presenting it as a special case of the second law can make it seem redundant, a mere preamble.
Like, why bother stating it separately?
Exactly. It risks obscuring the first law's true role, which, in some interpretations, is precisely to define the very context, the inertial frame, in which the second law can even be applied meaningfully.
Oh, okay.
Without an inertial frame, EFMA doesn't necessarily hold true, or at least becomes far more complicated with fictitious forces. So the first law isn't just EFMA when F is zero, it's the declaration that there exists a framework where that simple relationship can be observed.
In contrast, more conceptual mechanics textbooks like Klepner's state.
Yeah.
Newton's first law expresses that inertial reference frames exist. This interpretation emphasizes its fundamental definitional role.
Which is a very different flavor.
Yeah, totally different. So what does this all mean? The variation in how the first law is stated underscores a fundamental lack of a unified view, often introducing it as a mere preamble to the second law, which might detract from its independent importance. The textbooks that link it directly to inertial frames like Klepner's emphasize its fundamental definitional role, but even then, they often don't fully explain the nature of these frames or the challenges in finding them.
This leads us to a crucial point. What exactly are the core concepts embedded within the first law statement that generates so much discussion and diverse interpretation? The ambiguities stem from fundamental questions arising from the key terms themselves. Let's break it down by focusing on the key words in its formulation. Everybody continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it.
Okay, so let's start with everybody. When you say everybody, my immediate thought goes to something simple, like a ball. But what exactly does everybody refer to in the first law? Does it apply only to idealized point particles, or also to more complex, extended bodies like rigid objects, especially those undergoing rotational motion?
That's a great question.
If it includes rigid bodies, which parts of its motion are being described? For example, are we talking about its center of mass? Different parts might have different motion, so how does this universal statement apply without further clarification?
This ambiguity is crucial and often overlooked. Newton's laws are fundamentally formulated for idealized point particles.
Right, tiny dots.
Tiny dots. The behavior of extended systems or rigid bodies, like a spinning top or a complex machine, must be derived by applying Newton's laws to their constituent particles and making additional assumptions such as assuming rigidity or elasticity. The concept of the center of mass itself, which is often used to describe the motion of extended objects, is a derived concept.
It's not fundamental to the law itself.
Not directly. It requires applying the first law to individual point particles and then integrating their motions. If we want to use the center of mass at the level of the first law, we'd logically need a separate definition for it beforehand, which introduces another layer of complexity to what seems like a simple, universal statement.
That's a profound point, often overlooked indeed. Then there's the concept of force. What exactly does external force mean in the first law? How can we independently identify a body that is truly free from external forces?
The million-dollar question.
If we define force using Newton's laws themselves, for instance, saying force is what causes acceleration, Newton's second law, we run into logical circularity.
Yep, the circularity problem again.
If we need to observe motion to infer force, and we need the absence of force to define inertial motion, we're caught in a loop. It's a scientific chicken or the egg problem. Which came first, the inertial frame or the force? It just makes your head spin a bit, doesn't it?
It truly does. Without an independent way to detect the absence of force, the law struggles to be empirically testable in a pure sense. For example, how do we know if a feather in a vacuum chamber is truly force-free without observing its motion and assuming the first law holds?
Right.
If it moves uniformly, we say no force. If it accelerates, we say there must be a force. But that's using the law to define force, which is then used to test the law. It becomes a closed loop, weakening its power as an independent empirical statement.
And finally, the phrase uniform motion in a straight line. Relative to what frame or observer is this motion defined? How is a straight line defined? Are these concepts dependent on inertial reference frames, and if so, how are inertial frames themselves defined by the first law itself or independently? What appears straight in one coordinate system might be curved in a rotated one, so there's a coordinate dependence here. It feels like we need a ruler and a clock that are inherently straight and uniform to even begin.
Precisely. These ambiguities highlight the deep conceptual and practical challenges in understanding the first law. If addressed coherently, they could significantly improve the teaching of classical mechanics, moving beyond rote memorization to a true appreciation of its foundational nature. The questions of relative to what and how defined are central to the historical development of these concepts, as brilliant minds struggled to pin down what seems so simple.
History shows that brilliant minds have wrestled with these questions for centuries, leading to a fascinating evolution of our understanding of inertia. The understanding and interpretation of Newton's first law have evolved through history, influenced by key contributions and diverse perspectives from various scientists who helped clarify the concepts of inertia and inertial reference frames. It's a remarkable journey, really, watching how science refines its own fundamental terms.
It is. Let's start with Isaac Newton himself in 1687, who formulated the first law and boldly introduced the concept of absolute space as a fundamental unmoving reference for motion.
Absolute space sounds grand.
It was grand. He defined absolute space as an infinite, immutable, and uniform framework, and absolute time as a universal, uniform flow, independent of any physical body or measurement. These concepts allowed him to describe motion without dependence on specific objects and formulate universal laws of physics.
So, why did Newton feel he needed absolute space and time? It sounds very abstract, almost philosophical, especially for someone laying down the laws of physics.
He was driven by two core ideas. First, the Copernican principle, the idea that Earth or any other body has no special privileged place in the universe.
Okay, no special viewpoints.
Exactly. Therefore, motion shouldn't be defined merely relative to Earth or any other specific object which itself might be moving. Second, the desire for universality of laws, meaning physical laws should be valid everywhere in the universe, independent of specific bodies.
Right, the laws have to be the same everywhere.
If laws depended on the particular reference body, they would differ for each body, undermining the idea of universal physics. Absolute space and time provided an independent external framework, allowing Newton to state laws that applied universally everywhere for all time.
That makes sense for the philosophical need for universality.
Yeah.
But how did he structure this mathematically? What did this absolute space-time actually look like in his equations?
Mathematically, absolute space is a three-dimensional Euclidean space, which is what we typically imagine as empty space with fixed coordinates. Think graph paper, but infinite.
Got it.
Absolute time is a one-dimensional axis flowing uniformly. These combine to form what we now call a Newtonian space-time, where an object's position and time are precisely defined relative to these absolute frameworks. The concept of a straight line, in this context, requires an affine structure.
And a fine structure, what's that?
Think of it like this. An affine structure allows you to distinguish between paths that are truly straight and paths that are curving, even if you don't yet have a way to measure the precise distances or angles. It gives space a kind of flatness that defines straightness without needing a ruler yet.
Okay, it defines straightness itself.
Right. And for uniform motion, we then need ways to measure both distance in space, that's our familiar Euclidean geometry, with its metric for measuring how far apart points are, and intervals of time, a temporal metric for how long events last. These metrics are simply the mathematical tools that allow us to consistently define things like velocity as the ratio of distance traveled to time elapsed.
It sounds incredibly elegant in theory. But absolute space sounds, well, unobservable. How would you actually measure something against an invisible, unmoving framework? And weren't there problems with it?
And that's exactly the paradox of absolute space. Despite its theoretical importance, absolute space faced significant challenges from the very beginning. It's not directly observable, so how can motion be measured against something you can't see or touch?
Like measuring against ghosts.
Pretty much. Newton famously tried to prove its existence with his bucket experiment, where a spinning bucket of water showed a concave surface, even when the bucket itself was stationary relative to the observer. Newton argued this concavity demonstrated that the water was rotating relative to absolute space, not just the bucket.
Ah, the bucket experiment.
But critics like Ernst Mach later argued that the water was rotating relative to the distant stars, effectively proposing that motion is always relative to matter, not an empty absolute space.
Okay, so Mach offered a different explanation.
Yes. Another problem for Newton was that an infinite number of equivalent absolute spaces could exist, each shifted or moving at constant velocity relative to each other, yielding the exact same observable results. This undermined its absolute nature.
If there are infinite versions, it's not really absolute, is it?
Not in a unique sense. If you can't observe it and there's an infinite number of indistinguishable ones, what good is it as a truly unique absolute reference?
Acknowledging that observational problem, Newton proposed using fixed stars as a practical, observable proxy for absolute space and Earth's rotation for absolute time. This sounds more pragmatic, grounding the abstract in something tangible.
It was, for his time, a pragmatic compromise for astronomical calculations. It worked pretty well. However, this raised new philosophical and scientific questions. If motion is ultimately measured against material bodies like fixed stars, why the need for abstract, unobservable, absolute space and time in the first place?
Good point. Seems redundant.
And also, the choice of fixed stars seems arbitrary. There's no inherent reason for their privileged status. Why not Jupiter or a distant galaxy? Ernst Mach specifically criticized this dependence on material bodies, arguing that motion should be relative to the actual distribution of matter in the universe, a concept that later influenced Einstein's general relativity.
So this reliance on material proxies led others to try and define things more operationally without needing those abstract, absolute concepts. This is where Carl Newman comes in, right?
Exactly. Carl Newman, in 1870, proposed that laws of motion should be defined relative to specific physical systems, moving away from Newton's absolutes. He introduced the concept of an alpha body, a perfectly rigid, specified material body, as the reference for the first law.
An alpha body. So like pick a specific object.
Yeah, a defined, idealized, rigid body. Instead of absolute space, you'd use the alpha body to define your coordinate system. He also used the first law to define a timescale. If two free particles move with uniform velocities, the ratio of distances they cover in equal time intervals is constant.
Okay.
This fixed ratio could then be used to define a timescale independent of Newton's absolute time. This was a crucial step towards making physics definitions reliant on observable, measurable phenomena.
That's a significant step toward making the definitions more concrete and observable, moving away from unobservable absolutes. So you're building the framework out of the very things you're observing.
And Ludwig Lange, in 1885, built on Newman's ideas even further, bringing us closer to our modern understanding. He introduced the term inertial reference frames and provided an operational definition for them.
Ah, inertial frames. We hear that term a lot.
Yes, and Lange tried to pin down what it means operationally. He proposed that straight paths can be defined using the motion of free particles. This was his crucial insight. While the path of one or two free particles could be made to look straight by choosing a suitable, perhaps even weird, coordinate system.
You could always rig the coordinates for one or two.
Right, but the paths of three or more non-collinear free particles cannot all be made straight in an arbitrary coordinate system.
Wait, so you couldn't just choose any weird coordinate system to make things look straight anymore? What's special about three non-collinear particles?
Think of it like this. If you have one particle moving, you can always pick a coordinate system that makes its path look straight. If you have two, you can usually align your coordinate system along their motion. But with three or more, if they're truly free particles and their paths are not straight relative to each other, no matter how you twist or turn your coordinate system, you won't be able to make them all appear straight simultaneously.
Ah, okay. It provides a constraint.
Exactly. It provides a rigorous empirical test for identifying an inertial frame. Therefore, Lange asserted that an inertial frame is a coordinate system in which at least three non-collinear free particles move in straight paths, and the ratios of distances traveled by any two of them in equal time intervals remain constant, as per Newman's timescale.
So it's defined by the behavior of free particles themselves.
Precisely. This provides an operational, material-based definition of inertial frames without resorting to unobservable absolute space, making the concept empirically grounded.
These historical contributions demonstrate the gradual evolution of our understanding of Newton's first law. They not only help us grasp the law more deeply, but also laid the groundwork for subsequent advancements in theoretical physics, moving physics towards more observable and operationally defined concepts. It's like watching science learn to tie its own shoelaces more efficiently.
A good analogy. A slow, careful process of refinement.
We've journeyed through centuries of brilliant minds grappling with inertia, steadily moving towards more operational definitions. But despite all that progress, Newton's first law still harbors two stubborn, almost philosophical challenges that continue to vex physicists today. First, there's the challenge of empirical access.
Right, the practical side.
The first law describes a state where no external force acts on a body. However, in the real world, forces like friction, air resistance, and especially gravity are almost universally present.
Everywhere.
Finding a state completely free from forces is practically impossible. This makes it incredibly challenging to verify the first law empirically in a truly isolated environment.
It truly does. In a laboratory setting on Earth, we can minimize friction and air resistance, maybe go into a vacuum chamber, but gravity is always there, pulling on everything.
Can't shield from gravity easily.
Not in the Newtonian framework, no. Some propose using absence of net external force instead of absence of external force, but independently determining zero net force without referring to Newton's laws themselves, which creates that circular definition we talked about, is problematic.
Yeah, how do you know the net force is zero without seeing if the object accelerates?
Exactly. For example, how do you know if a magnetic force is perfectly canceled out by an electric force without looking at the object's motion and then applying Newton's laws to interpret it? You need to measure the forces, but how do you measure a force without knowing how it affects motion, which is what the laws describe?
This leads directly to the problem of logical circularity, which, for me, is one of the most fundamental problems in interpreting the first law. The first law is often said to define inertial frames where the second law, F-ma, holds. But then, inertial frames are defined as those where the first law holds. It's like trying to define a champion athlete as someone who wins races, but then defining winning a race as what a champion athlete does. You're just spinning your wheels, aren't you?
You've captured it perfectly. This is a deep philosophical knot. If we observe a particle moving at a constant velocity, how do we interpret it?
Right, what does it mean?
You have two equally valid yet contradictory interpretations. A, the chosen frame is inertial and no force acts on the particle, consistent with the first law. Or B, the chosen frame is non-inertial, but a fictitious force happens to create constant velocity.
Like being in a car smoothly accelerating, maybe. Things look weird.
Could be. We have no independent way to distinguish between these two scenarios without already assuming the definition of an inertial frame or the nature of forces.
And the same problem applies if a particle moves with non-constant or accelerated velocity, you can say. A, the frame is inertial, and a force acts on it, or B, the frame is non-inertial, and no force acts on it, but the acceleration is just an artifact of your chosen non-inertial frame.
Like the feeling of being pushed back in your seat when a car accelerates, is it a real force or just inertia relative to the accelerating frame?
Without an independent definition of force or an inertial frame, it's impossible to definitively determine which interpretation is correct. This leads to a lack of predictive content in the first law, perfectly captured by Eddington's sarcastic quote we mentioned earlier. Everybody continues in its state of rest or uniform motion in a straight line, except insofar as it doesn't.
Yeah, it becomes almost like a rule for bookkeeping, not a predictor.
It essentially becomes a statement that can't be wrong, but also doesn't really tell you anything new.
To address the unobservability problem of a force-free state, some, like Ernst Mach, tried what's called the large distances approach.
Okay, trying to fix the empirical access issue.
Right. The idea is that all forces, like gravity and electromagnetism, diminish with increasing distance. So a particle sufficiently far from all other bodies can theoretically be considered a free particle.
So the first law could be rewritten. There exists a set of reference frames called inertial frames, in which particles sufficiently far from all other bodies move with uniform velocity in straight paths. This replaces the abstract absence of force with a more concrete, albeit challenging, concept of sufficient distance, aiming for a more operational definition.
However, this approach faces its own significant challenges. Firstly, it's practically impossible to find a particle completely free from the influence of all other bodies in the universe.
Like we said, even distant stars have gravity.
Exactly. Long-range forces like gravity and electromagnetism truly extend to infinity, even if their strength diminishes. So, sufficiently far still means practically unreachable. Secondly, there's the ambiguity of sufficiently large distance.
How far is far enough?
Precisely. What exactly constitutes a sufficiently large distance? Forces like gravity never truly become zero, So defining a threshold is difficult and arbitrary. And finally, this definition is inherently approximate, which is problematic for the fundamental principles of a theory.
Right, foundations shouldn't be approximations.
Exactly. Approximations should typically result from a theory as solutions to its equations, not be foundational to its very definition. It feels like sweeping the problem under the rug.
Another subtle but critical challenge, which you hinted at earlier, is the very concept of body in the first law. Is it valid only for idealized point particles, or does it implicitly include extended bodies?
Back to the body problem.
Yeah. Consider a rigid body rotating in free space without external forces. Its overall motion might not be in a uniform straight line. Different parts of it are constantly changing direction. Or two oscillating bodies connected by a spring in deep space.
Good examples.
Newton's laws are fundamentally formulated for point particles. The behavior of extended systems or rigid bodies must be derived by applying Newton's laws to their constituent particles and making additional assumptions, such as rigidity or the principles of rotation.
This is a profound point often overlooked, and it highlights a foundational mismatch. The concept of the center of mass itself, which we often use to simplify the motion of extended objects, is a derived concept. It's calculated.
Not given up front.
Right. It requires applying Newton's laws to individual point particles within the body and then integrating them. If we want to state the first law at the level of a macroscopic body, we'd logically need a separate, independent definition for its center of mass, adding to the definitional burden.
Okay, so lots of issues still. Now let's consider a reformulation of the first law that tries to address some of these logical issues, even if other challenges remain. This version aims for logical coherence. There exist certain coordinate systems called inertial frames in which point particles that are isolated from all external influences move with uniform velocity in straight paths.
Okay, a tighter definition.
This version uses isolated instead of sufficient distance, which is more general, for example. It allows for the theoretical use of opposing charges to cancel electromagnetic forces, not just infinite distance.
While this version is certainly an improvement in terms of logical precision, challenges persist. Firstly, defining uniform motion and time. Uniform motion relies on a precise definition of time. How do we measure uniform time?
The clock problem.
Exactly. If the measuring device, like a clock, or the reference frame itself isn't truly uniform, what appears uniform in one frame might not in another. The definition of time, a constant flow, must logically precede the first law.
And what about straight path? Similarly, how is a straight path defined in a coordinate system? What appears straight in one coordinate system might be curved in a rotated or accelerating one.
Right. Straightness depends on your grid.
It feels like we need a pre-existing notion of straightness for our coordinate system, which is what the first law is supposed to help define.
And as previously mentioned, the isolation challenge remains, especially with gravity. Gravity's long range and pervasive nature means it cannot be fully isolated or eliminated. Even if you theoretically cancel out electromagnetic forces, gravity permeates everything with mass.
It's always there.
Always there. This makes the empirical verification of truly isolated particles extremely difficult, if not impossible, in any realistic scenario. It's the ultimate nemesis to the first law's ideal conditions.
We've hinted at it throughout this deep dive, but the pervasive presence of gravitational force is arguably the most fundamental challenge to interpreting Newton's first law.
It really is the elephant in the room for classical mechanics.
Inertial frames require systems isolated from external forces, but gravity, being long-range and universal, affecting all mass, simply cannot be completely isolated. In the real world, paths are never perfectly straight due to gravity's omnipresent influence.
Think about Galileo's famous inclined plane experiment, often cited as a precursor to the concept of inertia.
Yeah, the ball rolling down one ramp and up another.
Exactly. It showed that a body on a frictionless inclined plane would return to its original height on a second inclined plane. And if the second plane were horizontal, it would theoretically travel indefinitely. The implication was motion without external forces, pure inertia.
It's a classic thought experiment, one of the first things you learn in physics. But as you point out, this experiment was conducted on Earth, where gravity is always present.
Precisely. The paths observed, even ideally frictionless, are not truly straight. They are curved due to Earth's gravity. A ball rolling on a horizontal surface is still subtly following the Earth's curvature, or more accurately, being pulled downwards.
So even Galileo's ideal experiment wasn't really showing force-free motion.
Not in the strictest sense. It demonstrates that even in foundational experiments meant to illustrate inertia, the concept of a straight path, free from gravitational influence, is not empirically accessible. The idealized straight line is an abstraction, not a direct observation in a gravitational field. So the first law, in its purest form, describes something that practically doesn't exist in our universe.
So what do we do about this fundamental conflict between the omnipresent force of gravity and the ideal conditions of Newton's first law? This raises an important question. Does the first law truly make sense in a universe with gravity?
There are several ways to approach this, from practical compromises to deep conceptual reevaluations that completely redefine gravity itself. Let's look at option 0, the practical approach, which was effectively Newton's choice, born out of necessity.
Using the stars.
Right. He himself chose to use the fixed stars as a practical reference for absolute space and Earth's rotation for absolute time, even while holding his theoretical absolute space concept.
This approach worked remarkably well for describing planetary motion and earthly dynamics, which were Newton's primary concerns at the time, leading to incredible predictive power.
Yes, it was empirically successful for its time, no doubt about that. However, it introduces conceptual redundancies. Why define unobservable absolute space if we ultimately refer to material stars?
Right, the point we made earlier.
And it's arbitrary, as there's no inherent reason for the fixed stars to have such a privileged status beyond convenience. In this view, the first law becomes less of an independent, profound principle and more a special case of the second law, serving primarily to define where the second law holds. The term inertial itself becomes less about the fundamental nature of inertia and more about simply identifying suitable frames for practical calculations, for example, for designing a cannon or predicting planetary orbits.
Okay, so that's the pragmatic fix. But what if we want something more fundamental? If we cannot define global inertial frames perfectly due to gravity, and if the first law is so problematic, what if we just throw out the idea of special frames altogether? This would be option 1, abandoning global inertial frames.
It's getting radical now.
Yeah. This would mean reforming Newton's second law itself to be independent of specific coordinate systems. This would mean writing the second law in a covariant form, valid in any coordinate system, thus removing the need to define special inertial frames where it holds.
This is a radical shift in thinking, one that truly defines modern physics. It suggests that instead of desperately trying to find special frames where our laws work, we make our laws work in any frame, regardless of whether it's accelerating or rotating.
Wow.
This covariant form essentially means writing the law in a way that looks the same and works universally, no matter which coordinate system or viewpoint you're using. It takes the emphasis off needing a special frame for the laws to be valid.
This definitely raises a crucial point. Can we redefine concepts like force and mass in a way that doesn't depend on particular coordinate systems? It sounds like we're moving away from the very foundations we just explored.
That's precisely the challenge and the path taken by more advanced theories like general relativity. But now let's explore option 2. Gravity as geometry, not force. This is where it gets really interesting, and where the first law truly finds a profound reinterpretation that resolves its conflict with gravity.
Okay, I'm intrigued. Gravity as geometry.
Yes, the core idea is to introduce local inertial frames.
What are local inertial frames, and how do they resolve this conflict?
In small enough regions of space-time, it's possible to choose a coordinate system where the effects of gravity effectively vanish. Think of a freely falling elevator or a spaceship in orbit.
The classic astronauts floating scenario.
Exactly. Objects inside appear weightless and move in straight lines relative to the frame of the elevator or spaceship. This is often called a zero-G environment, but it's more accurately a local inertial frame. In these freely falling frames, gravity is not considered a force at all.
Wait, gravity isn't a force in a falling elevator.
Not in this view. An object in free fall is actually following a straight path, what physicists call a geodesic through curved space-time, rather than being forced into a curved path by an external force.
Wow, that's a completely different way to look at it. So if I drop an apple, it's not being pulled by a force, but rather following a curve in space-time caused by the Earth. Can you give us an even more tangible analogy to grasp what a curved path in space-time really feels like, since we can't see space-time? That's mind-bending.
Exactly. It is mind-bending. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip or a curve in the sheet.
Okay, I can picture that.
Now, if you roll a marble across the sheet, it doesn't get pulled by the bowling ball in the traditional sense. Instead, it simply follows the curvature of the sheet caused by the bowling ball. Its path looks curved to someone looking down from above, but for the marble itself, it's simply following the straightest path available on that curved surface.
Ah, the path of least resistance on the curve.
Precisely. In this analogy, the bowling ball is like a massive object, Earth, the rubber sheet is space-time, and the marble is the apple. The apple is simply following the straightest possible path, a geodesic through the space-time that has been curved by the Earth's presence. Gravity, then, isn't a force acting within space, but a manifestation of the geometry of space-time itself.
So what does this all mean? This radical shift suggests that the first law and gravity aren't in conflict, but rather gravity is an aspect of space-time geometry. Instead of objects following straight lines in a flat space and being pulled by a force, they follow curved paths, geodesics, in a curved space-time.
Yeah, you got it.
The force of gravity is simply our perception of these curved paths from a non-freely falling or non-inertial perspective. It makes so much sense of the problem of isolation. You don't need to isolate from gravity if it's just the shape of the road.
It truly does resolve that beautifully. This geometric interpretation leads to theories like Newton-Cartan gravity, which is a non-relativistic geometric version of Newtonian mechanics.
So it's like Einstein's idea, but for classical physics.
In a sense, yes. This means it still works within the classical framework where space and time are separate, not fused into a single four-dimensional entity like in Einstein's full general relativity. But critically, it explains gravity as a curvature of space and time within that classical framework, rather than as an external force acting in flat space. In this framework, the second law is rewritten covariantly, meaning it works in any coordinate system, and straight paths become geodesics in a non-Euclidean geometry. This beautifully solves the conflict between the first law and gravity by reinterpreting gravity as part of the geometry of space-time, rather than an external force.
It gives it a whole new lease on life.
Exactly. This perspective provides a unified and coherent description of motion, including the effects of gravity, without resorting to the problematic notion of global inertial frames. It allows the first law to survive, not as a statement about force-free motion, but as a statement about natural motion along the curvature of space-time. #outro.
What an incredible journey we've taken through Newton's first law, from its seemingly simple statement to the profound questions it raises about the very nature of space, time, force, and motion.
It's been quite a ride.
We've seen how historical figures grappled with its meaning, moving from abstract, absolute concepts to more operational definitions that could be tested and understood through observable phenomena, even as those tests proved elusive.
And we've uncovered how the omnipresent force of gravity presents a deep, enduring challenge to its empirical application, pushing us to consider radical reinterpretations where gravity itself is not a force, but a manifestation of the geometry of space-time, expressed through the concept of local inertial frames and geodesics.
Yeah.
It's truly remarkable how one seemingly basic law can open up an entire universe of complexity and new understanding.
Ultimately, this deep dive has shown us that even the most foundational principles in physics are not static truths, but living concepts, open to re-examination and deeper understanding as our scientific tools and philosophical perspectives evolve.
Absolutely.
It encourages you, our listener, to question assumptions and to always dig deeper into what seems obvious. The next time you see an apple fall, remember it's not just a simple pull, but a dance through the warped fabric of the universe.
A beautiful way to put it. And this raises an important question. If our understanding of straight paths and inertial motion is so intertwined with the very fabric of space-time, what does that imply about the journey of other fundamental laws, like Newton's second and third laws?
Good question. FEMA and action-reaction.
Right. What other geometric secrets might they hold, and how might our everyday understanding of push, pull, and reaction need to evolve as we dig deeper into the true nature of reality? Perhaps, like the first law, they too are less about forces in flat space and more about the intrinsic geometry of everything. Something to think about.